All right, e-learning day 4. Here are our notes on polars. So a polar graph is really a special kind of a parametric graph that has a specific coordinate conversion. So x is going to be the radius times the cosine of theta, y is the radius times the sine of theta, and then x squared plus y squared equals r squared. So if I think about a particular radius, I can go all the way back to when you learned SOHCAHTOA. And we can say that if this is theta, and that's the angle, and then r is the length of that radius, then the x coordinate would be, let's see here, the x over r would be the cosine theta, which tells us that x is r cosine of theta, and y over r would be opposite over hypotenuse would be the sine of theta. You can also say that the tangent of theta is y over x, the opposite over the adjacent. So that really gives you all the coordinate conversions there, and this is a special case of parametrics. All right, then we think about area in polar form. This is the formula that you're going to need to use, and I want to show you why that formula is true, but you don't necessarily need to be able to prove it again. You're just going to use it. So the integral from alpha to beta, that could just be a to b, but you know we're in polar, so we use some fancy Greek letters. 1/2 r of theta squared d theta. All right, so area of a circle is pi r squared. Area of a sector was theta over 360 times pi r squared. So it was a fraction of the circle. Like 180 degrees out of 360 was half of pi r squared. 90 over 360 was 1/4 of the area of that circle. Well, if we think in radians, then we're thinking that we have theta over 2 pi times pi r squared. Well, we can go ahead and we can reduce the pi's, and we get 1/2 theta times radius squared. Okay, so then what we're thinking is that if we have a region, we're taking individual little sectors of the circle, and we're finding the area of each little wedge as we go along, just like we did rectangles and we did slopes of secant lines and making them tangent lines, that kind of thing. So now this time, what we're doing is we're letting the change in theta go down to 0, and so then that's why we have 1/2 r squared and then d theta times that small tiny change in theta, adding all of those up as we go along. All right, that's where the formula comes from. So now we look at an example. Given that r equals 3 plus 2 cosine of theta, find the area inside that cardioid. Okay, so knowing how to graph these comes in handy. It's not the major focus, but it does sort of come in handy. So if I think about my unit circle values, and I think about when theta is 0, then the cosine of 0 would be 1, so 3 plus 2, that would give me 1, 2, 3, 4, 5. So when theta is 0, I get a y coordinate, not a y coordinate, but I get a radius of 5, so 5 units out. When theta is equal to pi over 2, then the cosine of pi over 2 is 0, so then it's 3 plus 2 times 0, or just 3. When theta is pi, then it's 3 plus 2 times -1, or just 1. 3 pi over 2 gets me back here to the same thing. And if I draw my cardioid, it ends up looking something like that. Okay. Find the area inside this cardioid. Okay, so I'm looking for the area inside that cardioid, and it actually took going through the whole entire unit circle to draw that cardioid. So that means that I'm taking my integral from 0 to 2 pi. That could change. There might be some polar graphs that it would repeat over themselves if you went from 0 to 2 pi, and you would change the limits of integration for something like that. And then I'm looking at 1/2 r squared, but I'm going to substitute in for r. D theta. Okay, so if I want to integrate this by hand, then I'm thinking 1/2, and what would that be, 9 plus 6 cosine theta and another 6, so 12 cosine theta, just expanding this binomial, right? Plus 4 cosine squared theta d theta. And then if I have to integrate that by hand, I'm going to go ahead and replace this part with 1 plus cosine 2 theta over 2. And we went ahead and we did that earlier on in the year, right? We talked about that identity. It's really often that you're going to find that these don't have to be integrated by hand. So if you were to put this in the calculator, for one thing, you could change to polar mode, and then the button that normally gives you x would give you theta, or if you didn't change it into polar mode, that would be fine too if you just replaced all the thetas with an x. Integrate that in the calculator, and you're going to get 34.558. All right, find the area inside the outer loop but outside the inner loop for r equals 1 minus 2 times the sine of theta. A lot of what we need to know about these polar graphs is going to be when do they cross the pole, and the pole is the origin, and that's whenever the radius is 0. So we want to know 1 minus 2 sine of theta. When does that equal 0? So 1 equals 2 sine of theta. Sine of theta equals a half. Now I'm thinking on my unit circle, the sine is a half, where maybe at pi over 6, and then again here at 5 pi over 6. Okay. Now I'm trying to think about how I want to draw this, right? And I usually make some kind of a table of values. So when theta is 0, then r is just going to be 1. When theta is pi over 6, then the sine of theta is 0. Sorry, so the sine of theta is a half, so then I get, yeah, r equals 0. Good. Okay. Maybe I want to go with pi over 2. In that case, I'm going to get a value of -1. Then I'm going to go with 5 pi over 6. And I can get 0. I'm going to go with pi. So I like to do the 4 points that are on the axes for sure, and then maybe a couple of others. So that's going to give me 1. 3 pi over 2 is going to give me a value of 3. And back to 2 pi is going to give me a value of 1. So I'm just trying to make this graph right here. So, all right, let's see here. All right, so 1 unit out, then I go up here, and right away by the time I get to pi over 6, I'm already back to 0. So just a little tiny piece happens there. And then after that, I get down to, at pi over 2, I'm at a radius of -1. So that looks like the point 0, 1, because I'm thinking that pi over 2 is up here, but I'm going -1 units along that line, which is how I get down here. Okay, then back to 5 pi over 6 would be like somewhere around this angle. I get back here, I get back to 1, down to 3, and back to 1. So something sort of along those lines. Okay. Well, if I take the whole integral from 0 to 2 pi of 1/2 times my r squared, that's going to color in the entire outer loop plus twice the inner loop. So if I want inside the outer loop but outside the inner loop, then I'm going to have to subtract, well, I don't really want blue again. I'm going to subtract 2 times the integral from pi over 6 to 5 pi over 6, because that's when I was drawing that inner loop, was really in between here, was the part of my table of values drawing that inner loop. 1/2 of 1 minus 2 sine of theta squared d theta. And of course this one was supposed to have a 2 as well. And if I do that on my calculator, I'm going to get about 8.338. I think that's enough for a video, and maybe I'll make a second one for